The question that I have is, what is ultimate settlement and how do we calculate it? So what have we learned so far? Well, let's consider the settlement curve for one load step. Let's say we go from 4 psi to 8 psi. I'm going to generalize these. So we start from a point where the weight ratio is E naught and the vertical effective stress is sigma V naught prime. We apply a vertical stress change of delta sigma z. The soil is going to go through the process of consolidation and eventually the weight ratio changes to E1 and the total vertical effective stress changes to sigma V naught prime plus delta sigma z. The settlement at this point is what is called the ultimate consolidation settlement. In other words, if you increase the vertical stress, the sample is going to experience this much of settlement eventually. It'll take some time, but it's going to get there. If you recall, in processing the consolidation data, you measure the settlement and then we converted that into the change in weight ratio using the proportionality rule, right? In applying these ideas to a field soil deposit, in order to calculate the ultimate settlement of a footing or an embankment or something like that, we kind of go backwards. In other words, we would know the change in weight ratio and we convert that into a settlement. And that settlement would be the ultimate consolidation settlement. Say we have a normally consolidated clay. The initial and the final stages are schematically shown here. If I were to take the weight ratio and the vertical effective stress at the initial stage and plot it over here, that point is going to plot right on the virgin compression curve because the clay is a normally consolidated clay, right? And then during the consolidation, the weight ratio is going to keep changing and eventually it's going to end up at 0.2. So that represents the final stage. The change in weight ratio is delta E and that corresponds to an ultimate settlement of S infinity. We call it S infinity because theoretically it's supposed to take infinite amount of time before the ultimate settlement happens, but in practical terms we can always come up with a finite time, and we'll talk about that in the next video. Here's a proportionality rule for calculating S infinity. So once we calculate delta E, we can find S infinity. Now the next question is, how do we calculate delta E? Supposing, say, we are given the compression index C sub C. First I take the weight ratio and the vertical effective stress at the initial point 1 and substitute them into the equation of the virgin compression curve and I get this equation, right? And you repeat that for point 2, I get this equation, all right? Subtract one from the other, we get E naught minus E1, which is delta E. So delta E works out to be this. So given the final stress, initial stress, and the compression index, I can calculate the change in weight ratio. Say we don't know the value of the compression index, but we know the value of the coefficient of volume change. So in that case, what you do is you directly apply this equation, which is from the definition of A sub V, and then delta E then works out to be A sub V multiplied by delta sigma Z, and that gives you this equation for delta E. And just a note that if you were to then calculate the S infinity, the ultimate settlement, that works out to be this. So we have a sort of a simple equation for the ultimate settlement in terms of the coefficient of volume change. The third possibility is that the data has not been processed yet. You just have the raw data. All you have to do is to go in and mark the initial and the final points right on the graph and measure delta E directly from the graph. What if we have an over-consolidated clay? Well, the extension of the above ideas to OC clay is fairly straightforward. We know the initial point is now going to plot on one of the swelling curves, right? Swelling lines. But whether the final point is going to plot on the virgin compression curve or the swelling curve depends on the change in the vertical stress. Supposing, say, it plots over here, all right? Then the total change in the weight ratio can be split up into two parts. A part that involves the swelling line and the part that involves the virgin compression line. So we'll call these as delta E1 and delta E2. So we can utilize the equations we derived earlier in order to calculate this. You just have to recognize the fact that the slope of the line, this line here is C sub S, whereas the slope of this line is C sub C. Here are the corresponding equations. Make sure you use the correct stresses in these equations. So when you calculate delta E1, we are applying the equation between points 1 and 3, and the stresses at these points are sigma P prime and sigma V naught prime. So those are the stresses that come in this equation. And similarly, when we calculate delta E2, we are applying the equation between point 3 and point 2. The corresponding stresses are this and this. So these are the stresses that come up here. Now you add the two to get the total change in weight ratio, which is what we need to calculate S infinity. If point 2 also happens to plot on the swelling line, then the equation for delta E1 is this, and there's no delta E2. So the next question is, how do we apply these ideas to calculate S infinity in the field? So what are the differences between a lab specimen and the field soil deposit? There are two specific differences. Number one, in a lab specimen, the initial vertical stress is constant across the thickness of the specimen, right? But it's not true in the field. It's not generally true in the field. And similarly, the change in vertical stress is constant across the specimen thickness for a lab specimen, whereas that is not true either for a field soil deposit. So with these in mind, let's consider a simple system first, where the soil deposit is subjected to a uniform vertical stress. In other words, the change in the vertical stress is going to be constant for all the layers up until the bedrock, and it's going to be uniform. Let's just say there are 4 layers above the bedrock. So I'll pick the midpoints of these layers and calculate the initial vertical stress at these points and assume that these initial vertical stresses represents the entire thickness of the layers. So for layer number 1, the vertical stress goes from sigma 1 0 to sigma 1 0 plus delta sigma z, and the weight ratio then decreases from E1 0 to E1, and so on. We can calculate the change in weight ratios by one of the 3 methods we talked about earlier, and then we can calculate the compression of each of these layers individually, sum it up in order to find the ultimate settlement of the ground surface. So here is the equation. So if you keep the thickness of each of these layers small enough, then our assumption that the initial vertical stress is constant across the thickness of these layers is not too bad. So if you want to increase the accuracy of your calculations, that's what you do. You subdivide the layers into thinner layers. While our assumption that the increase in the vertical stress is uniform across the thickness of these layers is directly applicable to situations involving, let's just say, preloading, it is not applicable to situations involving a footing loading or an embankment loading. In such cases, we need to first calculate the increase in stresses caused by those specific loadings. The changes in stresses produced in the sublayers by those specific loading cases, like for example, loading by a spread footing changes from point to point. It decreases with depth. There are specific theories we use for calculating these changes, and they are covered in separate videos.